The universe is a place of balance, teetering on the edge of chaos. From the smallest atom to the largest galaxy, everything exists in a delicate equilibrium. But push too far, and the cosmos snaps. A star's magnetic energy surges, unleashing a solar flare that lashes into the void. A distant supergiant fuses iron in its core, triggering a cataclysmic hypernova that tears it apart. A spinning magnetar fractures under pressure, releasing a gamma-ray burst that could sterilize entire worlds. These are cosmic tipping points, moments when the universe reaches its breaking point. Yet amid the chaos, there's often salvation, a subatomic safety net that pulls back from the brink. Nowhere is this more evident than in the most extreme objects known, neutron stars. Tiny, incomprehensibly dense relics of dead stars. Neutron stars are the universe's ultimate physics experiments. They push matter to the edge of oblivion, forcing us to question the very nature of reality. Today, we journey to their cores to ask, just how far can you push the universe before it breaks? Let's start with the stars. Celestial furnaces that power the cosmos. Stars live in a delicate balance between gravity, pulling inward, and fusion, pushing outward. But when that balance tips, the results are spectacular. Take a solar flare. Magnetic energy builds within a star's atmosphere, coiling tighter and tighter. When it snaps, it hurls plasma into space at millions of kilometers per hour. On our sun, these flares can disrupt satellites and power grids. On larger stars, they're even more devastating. Solar flares are like cosmic pressure valves. They release pent-up energy, preventing the star from tearing itself apart. It's nature's way of maintaining stability. Now consider a supergiant, a star hundreds of times larger than our sun. In its core, it fuses heavier and heavier elements, hydrogen, helium, carbon, until it reaches iron. Iron doesn't fuse, it absorbs energy, tipping the star past its limit. The core collapses in milliseconds, triggering a hypernova, a supernova's bigger, brighter cousin. The explosion scatters elements like oxygen and gold across the cosmos, seeding future planets and even life itself. Then there's the magnetar, a type of neutron star with a magnetic field 1,000,000,000 times stronger than Earth's. When pressure builds in its crust, it triggers a starquake, releasing a gamma-ray burst, a beam of energy so powerful it could fry anything in its path. Gamma-ray bursts are the universe's most energetic events. They're brief, but they carry the energy of 1,000,000,000 suns. They show us how fragile stability can be. These tipping points remind us that the universe is dynamic, always on the verge of transformation. But to understand the ultimate tipping point, we must explore the strangest objects of all, neutron stars. Neutron stars are the remnants of massive stars, born in the fury of a supernova. They're small, about 20 kilometers across, but so dense that a single teaspoon of their material weighs as much as Mount Everest. When a star 8 to 20 times the sun's mass exhausts its fuel, its core collapses. Protons and electrons merge into neutrons, packing matter so tightly that it defies comprehension. The result is a neutron star, a cosmic tightrope walker balancing on the edge of collapse. The surface is extreme. Gravity is 2 billion times stronger than Earth's. If you dropped a pebble, it would hit the ground at half the speed of light. Mountains, if they exist, are mere millimeters high, flattened by the crushing force. Neutron stars are like cosmic laboratories. They push matter to densities we can't replicate on Earth. Studying them helps us understand the fundamental rules of physics. But the real mystery lies deeper. A neutron star's structure is layered like an onion. The outer crust is a lattice of neutrons and atomic nuclei. Below that, the inner crust becomes a nuclear pasta. Strange structures like lasagna or spaghetti formed under immense pressure. Deeper still, the core is a realm of the unknown. Matter here is compressed to densities beyond imagination. Some theories suggest it's a sea of quarks, the building blocks of protons and neutrons. Others propose exotic particles or even a state of matter we haven't discovered. To put it in perspective, the core's density is like squeezing the entire human population into a sugar cube. This is where the universe tests its limits, where the laws of physics strain to hold. The core of a neutron star might force us to rewrite quantum mechanics or gravity. It's where ordinary matter becomes extraordinary, and we're only beginning to understand it. Many neutron stars spin at dizzying speeds, up to 700 times per second, earning the name pulsars. Their magnetic fields whip particles into beams of radio waves like cosmic lighthouses. These pulses are so precise they rival atomic clocks. But even here, tipping points loom. A glitch in a pulsar's spin can signal a starquake, where the crust shifts, releasing energy that ripples through space. The core remains the ultimate enigma. If a neutron star gains too much mass, it crosses a final tipping point, collapsing into a black hole, a point of no return where space and time break down. Neutron stars are the last bastion before that cosmic oblivion. Neutron stars are more than cosmic curiosities. They're windows into the fundamental nature of reality. By studying them, we learn how matter behaves under extreme conditions, how gravity warps space, and how the universe maintains its delicate balance. In 2017, astronomers detected gravitational waves from two neutron stars merging, confirming theories about gravity and revealing how heavy elements like gold are forged. These collisions are cosmic tipping points that shape the universe's evolution. Neutron stars bridge the gap between the very small, quantum mechanics, and the very large general relativity. They're key to unifying our understanding of the cosmos. From solar flares to hypernovae, from gamma-ray bursts to neutron stars, the universe is a story of tipping points and resilience. Each snap, each collapse reveals a deeper truth. Even in chaos, there's a subatomic safety net, a way for stability to endure. Neutron stars, teetering on the edge of oblivion, show us just how far the universe can be pushed before it breaks. They remind us that reality is both fragile and resilient, a delicate dance of order and chaos. Neutron stars, teetering on the edge of oblivion, show us just how far the universe can be pushed before it breaks. They remind us that reality is both fragile and resilient, a delicate dance of order and chaos. So, how far can you push the universe? To the very edge where matter transforms, where physics bends, and where new questions arise. Neutron stars are the ultimate test, the final barrier before cosmic oblivion. Yet in their extremes we find answers. Answers about the atoms that build us, the stars that light our skies, and the forces that hold it all together. The universe may snap, but it also endures, finding balance in the most unlikely places. As we gaze at the stars, we're reminded, we too are part of this cosmic tightrope, born from the same tipping points that shape the cosmos. Neutron stars, the universe's strangest creations, are a mirror to our own existence, a testament to the beauty of pushing the limits. How far can you push the universe? As far as a neutron star dares.